Welcome back to Talk Tensors. As always, we're diving deep into the latest and greatest in machine learning research.
Always exciting stuff.
Yeah, so today's paper is one you sent our way, and it really caught our attention. It gets at something so fundamental, like how do we actually know what these neural networks are really picking up on? Not just, getting the right answer, but truly understanding why.
It's a challenge that keeps coming up, right? We want to trust these models, use them in critical applications, but that means we can't treat them as black boxes. We need to open them up.
Absolutely. And this paper tackles a very specific problem. The way we often try to find the most important parts of the input for a model's prediction, well, they argue that the standard approach has some serious flaws.
Yeah, they take aim at maximum mutual information, or MMI for short, which has been like the go-to method for a while.
Right. So let's break this down for our listeners because MMI sounds a bit technical. Imagine you're reading a movie review and it says something like, "The acting was phenomenal and the story blew me away."
Classic positive review.
Exactly. Now, each of those phrases on its own gives you a strong signal that this is a good review. And the idea behind MMI is to find that part of the input that's most informative about the output. But here's the thing the authors point out. Once you've got one of those phrases, like phenomenal acting, MMI doesn't see much additional value in finding the other one, even though both clearly contribute to the overall positive sentiment.
That's the crux of their argument. This diminishing returns problem with MMI. Just because adding more input doesn't significantly change our prediction doesn't mean that extra stuff isn't important for getting a complete understanding.
It's like, you already have a good sense of why the review is positive, but you're missing part of the full picture.
Precisely. And they don't just make this point intuitively. They dive into the math and show that mutual information isn't always this nicely additive thing. Knowing one piece of the puzzle can actually make another piece seem less informative than it really is.
Okay, so that's the theoretical side of it, but they took this further, right? Tested it out with real data.
Oh, absolutely. They ran a whole bunch of experiments with different tasks, classifying beer reviews, hotel reviews. They even looked at graph data. And what they found again and again was that after a certain point, throwing more of the actual human annotated rationale at the model didn't make his predictions that much better or reduce the error significantly.
So the gains just kind of flattened out.
Yeah, they hit this plateau, and that really strengthens their case, that relying solely on MMI can lead you astray. You might miss out on crucial parts of the explanation.
So that brings us to the really cool part of this paper. If MMI has these limitations, what do they propose instead? And this is where they take a very different approach. Instead of asking how well a chosen rationale helps predict the outcome, they flip the question and ask, can the network even use this rationale effectively?
It's a really clever shift in thinking. They're not just focused on reproducing the prediction with a rationale. They're looking at the network itself and saying, hey, does this input actually align with what you've learned to do well?
Right, because a network might latch onto some spurious correlation in the data, get the right answer, but not for the reasons we think it is.
Exactly. And to get at this, they start digging into the network's capability space. And that sounds a bit abstract, but it boils down to this. The weights the network, those connections between its neurons, they define what kinds of patterns and relationships the network is really sensitive to. They capture its expertise, so to speak.
So if you give the network an input that fits those learned patterns, it's like it lights up, right? It activates those neurons strongly. But if the input doesn't really align with what the network has learned to do well, it's kind of like it's fumbling in the dark.
That's a great analogy. And the way they measure how well an input is being utilized is by looking at the norm of its representation within the network. Specifically, they focus on the L2 norm.
Okay, so they've identified a problem with MMI. They've got this new concept of looking at how well the network can use the input. And now they've introduced this mathematical tool, the L2 norm, to actually measure it. But let's step back and make sure we understand the whole story here. What were the main steps the authors took in this research?
They start by setting the stage, emphasizing why explainability is becoming so critical in deep learning. We're using these models for things like fairness assessments, detecting backdoor attacks, ensuring robustness. And they make this important distinction between explaining a model after it's made a decision versus building interpretability directly into the model itself. They call that self-explaining or anti-hoc.
And the framework they focus on is rationalizing neural predictions, right? RNP.
Exactly. So RNP models are designed to not only make a prediction, but also highlight which parts of the input were most important for that prediction. And that's where MMI has been the reigning champion. But then they systematically dismantle the case for using MMI as the only objective. They use those intuitive examples we talked about, like the movie review, and then they lay out the formal arguments showing that mutual information can be misleading because it doesn't always add up neatly.
And those experiments really back that up.
Right. All those experiments with different data sets and architectures showing that MMI plateaus, you stop getting much benefit from adding more of the true rationale. So they've established the problem, and then they introduce their solution, this norm to rationale method, N2R for short. It's all about leveraging the L2 norm of the input's representation within the network as a signal for how well the network can actually utilize that input.
So how does that work in practice? How do they train a model using this N2R approach?
It's actually pretty elegant. They have two parts to the model: the rationale extractor, which picks out the important parts of the input, and the predictor, which uses that extracted rationale to make the final decision. Now, in N2R, they train the extractor to maximize the L2 norm of the chosen rationale's representation. So the extractor is rewarded for picking out parts of the input that the network can really work with effectively. And at the same time, they're still training the predictor to make accurate predictions based on that extracted rationale using the standard cross-entropy loss.
So it's like a two-pronged approach. And they didn't just stop there, did they? They also explored combining their norm-based objective with the good old MMI.
Yeah, they figured that maybe MMI could still be useful early on in training to quickly identify some of the most obvious relevant parts of the input. And then the norm-based objective could kick in to refine that selection, making sure it's something the network can actually use. So they tested out a loss function that included both MMI and the L2 norm term.
Okay, so they've got the problem, the solution, and some variations on how to implement it. What happened when they actually put it all to the test? Did this N2R method actually work better than just using MMI?
The results were pretty compelling. Across most of the data sets they tested, whether it was text classification using GRUs and BERT or graph classification with GCNs, N2R consistently produced better rationales compared to human annotated ground truth. They used the F1 score to measure that. And here's the kicker. N2R was even competitive with and sometimes even outperformed a large language model, Llama 3.1 8B instruct, on those text rationale tasks.
Wow, so this simpler method that focuses on network utilization was able to hold its own against a huge LLM. That says a lot.
It really does. And their ablation studies, where they systematically removed parts of their method, further strengthened their argument. They showed that the representation norm, that L2 norm, kept increasing as you included more of the true rationale, unlike MMI, which tended to plateau.
So for our listeners who are really into the nitty-gritty of machine learning research, let's put this paper in a historical context. What were the key ideas that paved the way for this kind of work?
Explainable AI, or XAI, has come a long way. Early on, people were mostly focused on things like sensitivity analysis or saliency maps, basically trying to figure out which features a model was most sensitive to.
Yeah.
But as models became more and more complex, we needed something more interpretable, something closer to how humans explain their reasoning. And that's how we got these rationale-based frameworks like RNP. The idea was to have the model itself select the specific parts of the input that justified its prediction. And MMI seemed like the natural choice to train these models. It was all about finding the most informative subset of the input.
It made sense at the time. We were looking for information, right? That's how we explain things.
Absolutely. But this paper really highlights the limitations of that information theoretic perspective. What's interesting is that a lot of the previous work on RNP was about refining the architecture or adding regularization techniques, but they all still relied on MMI at their core. This paper breaks away from that and proposes a completely new way of thinking about rationale extraction.
And that idea of using representation norms, that seems like it came from a totally different area of machine learning.
It did. They drew inspiration from research on out-of-distribution detection, basically trying to figure out if an input is really different from the kind of data the model was trained on. And one of the key insights there was that learned features tend to have higher representation norms. So they cleverly applied that idea to rationale extraction, reasoning that even within a normal input, the parts the network can truly utilize will also have higher norms. It's a cool example of cross-pollination between different subfields of ML.
So to sum it up, The main takeaway is that while MMI has been a dominant force in rationale-based models, this paper exposes its flaws and presents a very promising alternative based on how well the network itself can use the input.
Exactly. It's about moving beyond just reproducing the prediction and really getting at what the network is attending to, what it's actually basing its decisions on. And that's crucial if we want to build truly trustworthy and interpretable AI systems.
Okay, so now for the fun part, our novel notions segment where we riff on the paper and think about where this could lead.
I love this part.
So based on this idea of probing a network's capabilities through these representation norms, what are some exciting research directions that this might spark?
Well, building on this concept of really understanding what a model has learned, especially a pre-trained model, imagine this scenario. You have a massive language model, like one of those huge ones everyone's talking about, and you want to use it for a very specific task, like analyzing legal documents from a particular historical period, or maybe sifting through medical texts from a certain era, something very niche. But you don't have a ton of labeled data for this specific domain.
That's a very real problem, right? We have these powerful general purpose models, but how do we best adapt them to specialized tasks?
Right. So here's the idea. What if we could create a kind of capability map for different parts of this pre-trained model? We could analyze the representation norms it produces for a wide range of inputs that are characteristic of our target domain, even if we don't have labels for them yet. And those features that consistently result in high norms across these domain-relevant inputs, well, those are the parts of the model that have already developed strong representations for concepts and patterns relevant to our task.
So it's like seeing what the model already knows about the domain.
Exactly. But here's the less obvious and potentially even more impactful part. We could also identify the gaps in the model's capabilities. Those areas where certain domain-specific inputs consistently lead to low representation norms, and that could inform our fine-tuning strategy. We might need to focus our precious labeled data on training those specific parts of the network more heavily. Or maybe augment our data with additional unlabeled examples that target those weak spots. It could even reveal fundamental limitations of the model's architecture for that particular task.
That's a really cool idea. It could make transfer learning much more efficient and targeted. What kind of impact could this have?
This kind of capability mapping could be a game changer for researchers and practitioners working with limited resources or in highly specialized domains. It could guide them in choosing the right pre-trained models, fine-tuning them effectively, and maybe even lead to the development of more domain-specific architectures. The chances of being able to create this kind of profiling method seem pretty good, building on the insights from this paper. Whether it would completely change how we do transfer learning is a bit harder to say, but it has the potential to be very impactful.
I love that. What other novel notions come to mind?
Okay, here's one that's more about security. We know that adversarial attacks are a big concern in machine learning. These are those carefully crafted inputs designed to fool a model. What if these attacks, at least in part, work by pushing the input into regions of the feature space that the network doesn't really understand well, regions characterized by those low representation norms we've been talking about?
So the adversarial input might not activate the network's learned capabilities in the way a normal input would.
Exactly. And even if the model ends up making the wrong prediction, the way it processes that adversarial input internally might look unusual.
Yeah.
So what if we could monitor the distribution of those representation norms across the different layers of the network? If we see an input that causes a sudden drop in norms in those crucial intermediate layers, even if the final classification seems plausible, that could be a red flag.
So even if the model is tricked into giving the wrong answer, we might be able to detect it based on how it's internally processing the data.
Precisely. And this could lead to a whole new class of adversarial detection methods that go beyond just looking at the input or the output. They'd be looking at the guts of the network, at how it's actually engaging with the data.
That's fascinating. Are there any potential downsides or limitations to this idea?
Well, one challenge is that really sophisticated attacks might also try to maintain high feature norms while still being misleading. So it might not be a foolproof detection method. However, even if it's not perfect for detection, it could still give us valuable insights into how those adversarial attacks actually work. By seeing which layers or features are most susceptible to these norm-reducing perturbations, we can learn a lot about a model's vulnerabilities and potentially design better defenses. So the chances of this being a silver bullet for detection are maybe moderate, but the potential for it to help us understand and mitigate these attacks is definitely high.
These are some really thought-provoking ideas. It's amazing how a new perspective on understanding neural networks can open up so many possibilities.
It really highlights the exciting, dynamic nature of machine learning research. There's always something new to discover, and it often comes from challenging our assumptions and looking at things from a different angle.
If you want to dive deeper into the technical details and the experiments they ran, we've got a link to the paper in the show notes. Thanks for joining us on Talk Tensors. We hope this conversation has sparked some new ideas for you. And be sure to tune in next time when we'll unpack another cutting-edge piece of machine learning research. And remember, our Novel Notions segment is just the beginning. Take these ideas and run with them.
Absolutely. Keep exploring.
See you next time.
See ya.